Have you ever heard of a tardigrade? They are some of the most amazing animals on our planet, and they are also some of the smallest. You would need a microscope to see one. These tiny creatures, often called water bears or moss piglets, are famous for being incredibly tough. They can survive in places where almost nothing else can live. They can handle being boiled, frozen solid, zapped with radiation, and even launched into the vacuum of outer space. Because they are so good at surviving, scientists are very curious about them. They want to understand the secrets that make these little animals so resilient. This incredible toughness has led some scientists to ask a very big question. They wondered if a tardigrade could survive being part of an experiment in the strange world of quantum physics. This part of science studies the tiniest things in the universe, like atoms and the particles inside them. The rules in the quantum world are very different from the rules we see every day. Things can be in multiple places at once, and they can be connected in mysterious ways over vast distances. It's a world that is usually reserved for non-living things, so bringing an animal into it was a very bold and exciting idea for these researchers. The goal wasn't just to see if the tardigrade could survive, but to see if it could actually become part of a quantum system. Imagine connecting a living thing to the fundamental building blocks of reality. The scientists wanted to see if they could link a tardigrade to something called a qubit, which is the basic unit of a quantum computer. This would be a huge step in understanding the line between the living world we know and the bizarre, invisible quantum realm. Could a complex, multicellular animal truly interact with the world of quantum mechanics in a meaningful way? This question was the starting point for a fascinating and controversial experiment. Bringing a tardigrade into this kind of experiment is like asking an astronaut to walk on a planet made of ideas instead of rock. The conditions required for quantum experiments are extremely harsh, far beyond what even most tardigrades have ever faced. It involves temperatures colder than deep space and pressures lower than a perfect vacuum. The scientists knew that the tardigrade would have to enter a deep state of suspended animation called cryptobiosis to even have a chance. This is a special survival state where the tardigrade turns off all its life processes. It becomes like a tiny living piece of glass, waiting for conditions to get better before it comes back to life. The experiment itself was a journey into extreme cold. First, the scientists took a tardigrade and slowly cooled it down. They brought its temperature to just a tiny fraction of a degree above absolute zero, which is the coldest temperature possible in the universe. At this temperature, almost all motion stops. They also put it in an extreme vacuum, removing nearly all the air around it. This process put the tardigrade into its protective cryptobiosis state, a deep hibernation that allowed it to endure these incredibly harsh conditions. The little animal was essentially frozen in time. Its biological functions paused for the next step of the experiment. Once the tardigrade was prepared, it was placed onto a very special piece of equipment, a superconducting qubit. You can think of a qubit as a quantum version of a computer bit. While a normal computer bit is either a 0 or a 1, a qubit can be a 0, a 1, or both at the same time. This qubit, which we can call qubit B, was part of a tiny electrical circuit. The tardigrade, sitting on top of it, acted like a small speck of dust, slightly changing how the circuit worked. Specifically, its presence changed the natural frequency or the rate of vibration of qubit B. The next step was to bring in a second qubit, which we can call qubit A. The scientists then connected qubit A to the system that contained qubit B and the tardigrade. They watched very closely to see how the frequencies of all three parts, qubit A, qubit B, and the tardigrade, interacted with each other. The researchers reported that they saw the frequencies of all three components shift together in a way that, they claimed, suggested they were all linked. They believed this shared behavior was evidence that they had created a single connected quantum system made of two qubits and one whole animal. Based on their observations of these connected frequencies, the scientists made a very big announcement. They claimed they had successfully achieved quantum entanglement between the tardigrade and the two qubits. This would be a historic achievement, as it would be the first time a multicellular organism had ever been entangled. The idea that a living creature could be linked in this deep quantum way to a piece of hardware was astonishing. The paper they published with their findings quickly spread through the scientific community, sparking a lot of excitement and discussion about what it could mean for the future of biology and quantum physics. It is very important to understand what the scientists were actually claiming. They were talking about something called quantum entanglement, not teleportation. You might have seen teleportation in science fiction movies, where a person or object disappears from one place and instantly reappears somewhere else. That is not what happened here. Quantum entanglement is different, though it is just as strange. It's a special connection between two or more quantum particles. When particles are entangled, they become linked in such a way that whatever happens to one instantly affects the other, no matter how far apart they are. Albert Einstein famously called it spooky action at a distance. So the claim was not that the tardigrade was beamed from one place to another. Instead, the researchers believed they had created a spooky link between the living animal and their quantum computer. If this were true, the state of the tardigrade would be directly and instantly tied to the state of the qubits, and vice versa. It would mean the tardigrade had, for a moment, stopped being just a classical object and had become part of a larger, interconnected quantum entity. This is a mind-bending idea because we normally think of living things as being separate from this strange quantum behavior. We don't see people or animals existing in two states at once. However, many other scientists were not convinced by the experiment. As soon as the results were published, experts in quantum physics began to raise serious doubts. A major criticism was that the experiment didn't really measure the quantum state of the tardigrade itself. Instead, it only measured the qubit's frequency. Many physicists argued that you could get the exact same result by placing a tiny, non-living speck of dust on the qubit instead of a tardigrade. The dust would also change the qubit's frequency in the same way, through normal classical physics, not through any spooky quantum connection. These critics explained that for real entanglement to be proven, the experiment would have needed to show that the tardigrade itself was in a quantum state, such as being in a superposition of two different states at once. But the experiment didn't do that. It only showed that the tardigrade acted like a small object that influenced the qubit it was touching. This is an expected and well-understood electrical effect, not necessarily a new quantum discovery. Because of these strong doubts and the fact that the paper has not been successfully peer-reviewed, most of the scientific community does not accept the claim that the tardigrade was truly entangled. While the debate over the quantum entanglement claim continues, the experiment did give us one clear and amazing result. It confirmed, once again, just how unbelievably durable tardigrades are. One of the tardigrades used in the experiment survived the entire process. After being cooled to near absolute zero and held in a vacuum for 420 hours, that's over 17 days, the scientists warmed it back up, added water, and watched as it returned to life. This set a new record for the survival of a tardigrade in such extreme conditions, pushing the known limits of life even further than we thought possible. This incredible feat of survival is, in many ways, just as scientifically important as the quantum claim. It shows that a complex, multicellular animal can withstand the kind of environment needed for cutting-edge quantum physics experiments. This was something many biologists were not sure was possible. The fact that the tardigrade could be brought back to a normal, active state after being treated like a piece of inanimate matter is a powerful testament to the unique biology of these creatures. It opens the door for future experiments that could safely use tardigrades to explore the boundary between living systems and the physical world. The experiment, even with all the controversy, pushes science into new and exciting territory. It forces us to ask deep questions about what it means to be alive and where the line between the classical world and the quantum world truly lies. Can a living organism be put into a state of quantum superposition, like the famous thought experiment of Schrödinger's cat, which is both alive and dead at the same time? Or is there something special about life and consciousness that prevents it from ever entering this strange realm? These are no longer just philosophical questions, they are becoming questions that we can actually try to answer in a laboratory. Looking forward, this research inspires a whole new set of investigations. Scientists will now work on designing better experiments that could more definitively test for quantum effects in biological organisms. They will need to find ways to measure the quantum state of the organism itself, not just its effect on the equipment around it. Whether or not this particular experiment successfully entangled a tardigrade, it has started a fascinating new chapter in science. It has built a bridge between the worlds of biology and quantum physics, and we are only just beginning to see what strange and wonderful things we might find as we start to cross it.